Hello chemistry students, and welcome to the review for the Unit 8 test. You should have the review sheet. It looks like this. And I'm just going to jump right in and go over it. The first section is about why do some molecules stick together more strongly than others. And the first question. A molecule with two distinctly charged ends is a... And of course, the answer to this is a dipole. Right, di means two, pole refers to the polarity, and when we say charged, we're talking about the pluses and the minuses. Alright, B. In a nonpolar covalent molecule, the electrons are shared equally, are shared unequally, are not shared at all, are not involved in bonding. Well, nonpolar by definition means that they are shared equally. And if we look here, right, we see it right here. And we also see it right here, where the electrons are shared equally. When they're shared unequally, then we have polar covalent bonds. Okay. Which of the following bonds exhibits the greatest electronegativity difference? Okay, so difference means subtraction. And the way we do this is we take the numbers in the table, for example, lithium and fluorine, and we subtract them. So fluorine is 3.98. So I'm sorry, here's lithium and fluorine, 0.98. Right, and we subtract them and we see the difference is 3.0. Right, so the difference on this one is 3.0. That's pretty big. Alright, and look at some of the other ones. Let's do, that one might be the highest, right? Because those are pretty big difference. Let's try just one more. Let's do LiO. So lithium and oxygen. Here's oxygen. And that's 3.44. 0.98. Okay, change that to a 3, carry the 1, that's a 6. That's a 2. 2.46. Alright, so it seems like so far 3 is the biggest. So let's take a look at LiCl. I'm sorry, HCl. So H is 2.1. Chlorine is 3.16. Yeah, that's nowhere near 3. And then magnesium and iodine, 1.31, 2.66. Yeah, that's nowhere near 3. So clearly the biggest one is A. Okay, so again, the way I did that is I just looked at the numbers in the table and I subtracted them. Okay, and that's how I tell the electronegativity difference. Two atoms with an electronegativity difference greater than 2.0 form a bond that is what? Well, that refers to this table here. So electronegativity difference tells us what kind of bond. If the difference is greater than 2 or 2.1, we're going to be in the ionic range. Okay, if it's between 0.5 and 2.0, it's going to be polar covalent. If it's less than 0.5, it's going to be nonpolar covalent. So for example, this LiF would be ionic because it's greater than 2 or 2.1. So if it's greater than 2.0, right, that's going to put us right in the ionic range. Ooh, wait a minute. Ionic, we have two ionic ones. All right, so it can't be this one. Is it because electrons are shared in their ionic or because electrons are transferred? Well, if you remember back to the lesson on polar bears and penguins, what we saw about them covalent bonds was that covalent bonds are sharing. But when we get to ionic, the difference is so big, the electronegativities between atoms are so different that the bond's called an ionic. In the case of an ionic bond, the electron of one atom is completely given up. All right, that's because the polar bear is so much stronger than that other penguin that the penguin can't hang on. So the answer then would be C. Okay, it's important to know that ionic bonds are a transfer of electrons. Sharing is covalent, so it's definitely not A. Okay. So let's see. So the diagrams here refer to this table. And you're going to see a table like this on the test. How is the bond formed? Polar covalent versus non-polar covalent. Well, they're both a sharing of electrons, but polar covalent is an unequal sharing of electrons between two atoms, whereas a non-polar covalent is an equal sharing of electrons between two atoms. Excuse me a sec, it's going to take me a minute. One similarity is that both polar covalent and non-polar covalent bonds are a sharing of electrons between two atoms, right? Covalent is like cooperation, it's a sharing. One difference is that because polar covalent bonds share electrons unequally, they create partial positive and negative ends of the bond, right? So we see the partial negative and the partial positive right here. Okay, so that's the difference between the two. Which of these is non-polar, carbon dioxide or water? Well, we can tell from the diagram here that water is polar because it has these partial positive and negative ends. And carbon dioxide is a non-polar molecule. If you didn't know, what you'd need to do is to draw out the molecule, drawing out the structure. So here, non-polar would be CO2. Now, why is CO2 non-polar? The way we tell, and this should be on your cheat sheet and on your outline. Let's see. Sorry about that. It's on this one. Right here. So the way we can tell is that for something to be nonpolar, it's either got completely nonpolar bonds or polar bonds that are symmetrical, meaning they cancel each other out. For it to be polar, they have to have both polar bonds in an asymmetrical shape. So let's see. If we look at water, why is water polar? Well, water is polar because it's got polar bonds and it's got this asymmetrical bent shape. Carbon dioxide has polar bonds, right? These C to O bonds are polar, and we know that they're polar anytime you have atoms that are different, elements that are different, they're going to be some polarity. So oxygen is different than carbon, so each part of this is going to be polar, but because they're 180 degrees apart, they cancel each other out. Each oxygen pulls with equal strength on the carbon, and it's like a tug of war where the two people are exactly the same strength. They cancel each other out. So in writing, I would say it has polar bonds, but the symmetry of the molecule, and it means the CO2. It has polar bonds, but the symmetry of the molecule means those polar bonds cancel each other out. Okay, part 2. Water as an example. How does its stickiness affect our world? So why does water beat up on a penny? Okay, and this refers back to, I didn't say it, to the lab activity where we did this in the lab. And the hydrogen bonding forces between water molecules cause cohesion, which is the strong sticking together of the water molecules. Molecules at the surface feel a pull towards the center, causing the rounded shape. goes back to this thing we did right here around surface tension. Now, it's perfectly fine to use the term surface tension, but you've got to make sure that you explain what it is in terms of the sticking together of the water molecules caused by the partial positive and negative charges. You got to show that you know what surface tension is. If you just throw the word out, there's no indication that you understand it, so you won't get the credit. All right, and why does water rise up a capillary tube? Okay, that's the same lesson. All right, why does it rise up there? Well, here what we said was water sticks to other polar substances, and the walls of the capillary tube have partial charges that attract the water molecules. So, saying the same thing, the hydrogen bonding forces between water molecules and polar glass cause adhesion, which is a strong sticking together of water molecules to the glass. Molecules at the surface, oops, that's not supposed to be there, sorry about that. Okay, so that's that section. So when we get to the test, you know, we did do 2 other tests, so make sure that you know the other tests. I just didn't have room to put all 4. So the other 2 tests that we did, let's see. And we talked about sponges. How did the sponge work? Well, the sponge must have material that has the partial positive and negative charges, and the water is attracted to that. Ice cube floats because the molecules in the solid are farther apart than the liquid, so the liquid's more dense. That's why ice floats. Okay, and like dissolves like. We said that polar things tend to dissolve in polar things, and the reason why is that polar molecules are strongly attracted to each other. And so the polar things will stick together and kind of ignore the non-polar things. Again, please go and review this lesson if this doesn't make sense, so that when you want to dissolve a polar thing like sugar, you would want to use a polar liquid, because polar things tend to dissolve in polar things. Okay. So how does the stickiness of molecules explain why some things have a smell and others don't? All right. Small nonpolar molecules. Okay, remember, small nonpolar molecules may fit into receptor sites, but they won't cause a smell. If you would go back to our lesson here, right, where we looked at the attraction of the molecule to the charged plate. See, that would be this one. Right, and we looked at how these things would orient themselves towards the charged plate. What we saw in each case was that for the polar ones, right, this was a non-polar one, so it didn't do it, we would have the positive part of the molecule interacting with the negative part of the charged plate, because the positives and negatives interact. And that's what we saw. Right? And when we looked at the simulation here, we saw that the positive part of the smelly molecule would interact with the negative part of the receptor, and that positive-negative attraction is what causes them to pull together. When we looked at the simulation where the molecule didn't have the positive charge, it didn't go into the receptor because it didn't have that pull, and it wouldn't actually trigger the smell. All right, so small nonpolar molecules do fit into receptors, but they don't trigger them. Small polar molecules will smell because they fit into smell receptors and do trigger them, right? Because of those positive and negative, excuse me, because of those partial positive and negative charges. I'm gonna add that. Oops. their partial positive and negative charges. Okay, back over here. Right there. Medium-sized molecules. Well, medium-sized molecules evaporate easily to become a gas, and so they will have a smell. But large molecules, large solid molecules with 20 or more carbon atoms, don't evaporate. If they don't evaporate, they can't get to your nose. They can't get to your nose. They can't trigger a smell. Same thing is true of ionic substances, right? Solids, solid molecules don't evaporate, so they can't cause a smell. Metallic substances, well, they're solids. Solids don't evaporate, so they can't cause a smell. Covalent network substances, such as like diamond, sand, okay, they don't evaporate, so they can't cause a smell. All right, so remember, the two kinds of molecules that do smell are small polar molecules because they trigger the receptors, and medium-sized molecules because they evaporate easily. Okay, so again, make sure to review all of the lessons that we had in this unit because there's going to be more on the test than would fit on this 2-page review. The test itself, I think, is 5 pages. I didn't want to make a 5-page review, but it's similar to this. But just make sure you review all of the material, and if anything that I did on here doesn't make sense as far as how I got to the answer, please do ask in class. And I hope you found this helpful, and let me know how I can make these more helpful for you in the future. Thanks.